An area of concern when we're rigging this motor is the battery cables. Now, on a lot of center consoles, the batteries are going to be mounted up in the console, but the motor may only come with a 10 or 12-foot length of battery cables. Clearly not enough to get up to where the batteries are. So it's a common rigging procedure to mount power posts in an area very close to the engine and then run those battery cables from the engine to those posts and then run another set of battery cables from the posts up to the batteries. Now, this is an older two-stroke 150 and the boat is capable of having a 200. So let's say, okay, hey, listen, I'm going to put a 200 four-stroke on there. So two factors here. Four-strokes have higher compression, they're larger engines with camshafts, they need a lot more amperage to get the motor to crank over. So it's going to come with a fairly large set of battery cables that some people would just go and put to the post and say, I'm done. But the question is the existing wire from that post up to the battery adequate for the amount of length and voltage drop to get that motor to crank over? And if they're inadequate, we may have some cranking issues or voltage drop issues. So we need to consult with the manual and find out what is the minimum wire gauge size that we can have for extending the battery cables. Okay, another area is to check for clearance with the steering. A lot of people, when they're repowering a boat, buy a transom toughener, or they fabricate a aluminum plate to go on the transom to help, spread the load of maybe the heavier engine going on an older boat. They're worried about the transom possibly being a little weak. Typically not a problem with this type of steering system, this mechanical cable type steering. The motor can tilt up without hitting or having any issues. But when we have hydraulic systems, we have that cylinder laying out here. You've got to remember that as we tilt up the motor, what's going to happen is this cylinder is going to move forward too. And what happens a lot of times is that the cylinder comes down and actually hits that plate. And since the cylinder can't move anymore and the motor's being tilted up hydraulic, a lot of times it starts tweaking the brackets, especially the tiller arm that's underneath. And in extreme cases, the tiller arm can be bent. Hi, I'm Rob Barenwick from the American Boat and Yacht Council, and today we're going to show you how to test this power pedestal to confirm you have the appropriate power going on to your boat. With me today is Ed Sherman, who is the author of many books on marine electrical systems, as well as the Vice President of Education for the American Boat and Yacht Council. So, Ed, what's in store for today? We're going to do some testing here with a tool that you really like to use.
Yeah, we're going to show you how to use several tools that I've been using for some time now to confirm power integrity, getting on board a boat, as well as a tool that I use to look for ground fault leakage that is directly associated with a lot of the in-water shock hazards and in-water shock deaths that we've seen and had experience with around the country. I want to preface everything though by saying that The tests that we're going to perform are, they actually go a little bit beyond those prescribed by the National Fire Protection Association, NFPA, in their electrical codes applying to marinas. Their standards quite specifically state that these dock pedestals need to be checked and their integrity confirmed at least annually. And they get very specific about things that need to be tested. Ground integrity, looking for frayed wires, things of that nature. We're going to perform more tests than they actually demand, but I will tell you that if you're a marina operator, you really need to take this testing, this annual confirmation, seriously. Now, the things that we're going to show you how to do today, you can do pretty easily with the tools that we're going to use, but I would add that if you do find anything wrong for legal reasons, the most appropriate action would be to bring in a licensed electrician to minimize any liability risk on your part. So with that said, Rob's going to start using these tools, and we'll look at what it can do and what's implied by the various tests that he's going to make.
So our next test is another right-hand arrow. This one, it looks like it's peak voltage, 166.7 volts. So what is this telling me?
Okay, peak voltage is an interesting and kind of important value. You're actually measuring, because this ideal short test is measuring values at true RMS, which is acronym for root mean square. In electrical engineering, that's an important value. So we have our measured peak, and we're going to compare that to a theoretical peak. And your theoretical peak can be derived by taking your initial voltage reading, which was, help me, 116?
Yeah.
And you're going to measure that time, or multiply that times 1.414 to get what the theoretical peak should be with a perfect sine wave. So you compare the theoretical peak with your measured peak, and if there's anything more than about a 2 to 3 or 4% differential, it's indicating harmonic distortion in the power feed coming to the boat. Excessive harmonic distortion can be the cause for noise in things like audio amplifiers or funky screens on flat screen televisions and things of that nature. Mm-hmm. Okay. So it's a pretty good test using relatively inexpensive equipment. Harmonics analyzers on their own are priced in the $3,000 to $4,000 range, so it's not a tool that everybody's going to want to run out and buy next week. This gives you a relatively inexpensive way to at least get a sense for if there is excessive distortion.
All right, let's see what we've got next here. Okay, so this one is for our frequency. It says we're running 60 hertz. So can you tell us what is that?
In my experience, testing frequency delivered by utilities around North America, you're never going to see it off. I've never found it to be deviated from the 60 hertz. Okay. That said, let's say you were using this tool to check the output from an AC generator installed on a boat, which it's quite useful for doing that too. Any variation in frequency is going to be implying that you've got an RPM governor related issue with that generator, and it's going to need some adjustment. 60 hertz should be 60 hertz. The tolerance, again, from the ABYC standard is plus or minus 5%, but I will tell you that that is a very high number in today's world. Most electronically controlled AC generators available in our marketplace today for the marine service are going to pretty much assure you 1 or 2% accuracy to that 60 hertz frequency value, and they do achieve it.
So testing that generator will just be taking this unit and bringing it on board, running the generator and plugging it into an outlet that's on board to test and confirm frequency.
Absolutely. As long as that receptacle is supplied power by the AC generator when it's switched to generator mode on the boat, you can use it in that way. Yep.
Okay. So I can use this to test stuff on the dock and on the boat. That makes it really convenient.
Yep. It's a very valuable tool for testing AC systems.
So we've got this sacrificial anode, and just because we take this sacrificial anode and bolt it on this motor somewhere, that doesn't ensure it's going to work. So in order for this sacrificial anode to protect anything, it has to be electrically connected either through a wire or mechanically bonded, bolted to the part we are trying to protect. So let's take a look at this anode right here. It's physically bolted mechanically to the gear case. All right, but the gear case and the midsection are separated here. I'm not guaranteed that we have perfect connections to there. There might be some corrosion. We put grease on the bolts, so we're not guaranteed any connection through there. So if we want to guarantee that we definitely have continuity, a lot of times you'll see the use of bonding wires, and you may see these little tiny stainless steel wires and connectors in various parts on the engine. Now we've got another anode that's down here, and this anode is really to protect the transom bracket and in most cases the trim system. So a lot of times this anode is not going to be able to protect the gear case. And here's a classic issue. You've got a motor that doesn't tilt up out of the water all the way, and some of the gear case, that lower bullet, is left in the water. All right, now remember, that's sitting in the electrolyte. We have dissimilar metal, so we know we're going to have corrosion. What's going to protect that gear case is going to be the anode. But now with the motor tilted up out of the water, that anode is out of the electrolyte, so it's not affecting, all right, anything. So this part of the gear case now is not being protected at all. So you'd say, well, we've got this anode in the water down here. And again, it comes down to that bonding and continuity, is that anode is protecting this bracket. But this bracket sits on plastic bushings. And this bracket has bushings in here, and then this bracket's attached to the motor through motor mounts that isolate it. All right, so we're not guaranteed that that anode is actually grounded and mechanically connected to this gear case. Right, so there's a good chance that this area is going to corrode. So what we're going to do is talk about ways we can check to see if these anodes are functioning and if certain parts are connected into the system. Okay, we've got a Mercruiser Bravo 1 here, stern drive, and what we're talking about is the type of corrosion system it has. This motor has actually two different types. it has sacrificial anodes on it, but it also has that impressed current system we've been talking about. And the impressed current system, the device actually is mounted down below here under the transom assembly. And besides that, there's also the controller, which is a small little module that's up here on the engine. Now, the module has power and ground from the battery going to it, and has 2 wires that come off this controller and go down to the reference electrode down here. So we've got these different anodes that are above the propeller and on the trim cylinders, and one on the front of the drive. So you might be saying, well, why do we need anodes and an impressed current system? The whole idea here is the anodes take up a lot of the load, but think about this outdrive. There's a lot more metal in the water now as compared to an outboard. An outboard, when we tilt it up, we can get a lot of that metal up out of the water. Not so much with the stern drive. I mean, if the water line is here, we still have a pretty good amount of metal underwater. And we've got the similar metal, don't forget, we've got the stainless steel fasteners, these lines. So we need to have more anodes because there's more physical metal to protect. Now, because there are a lot of variables with corrosion, depending on where this boat moves, the rate of corrosion could change pretty dramatically. And that's where the impressed current system comes in nicely, is because with its controller, it can monitor the voltage in the water moving between the metals and add more voltage to get us in the appropriate range. And depending on where the boat goes, that may change due to the salinity of the water, the temperature of the water, the movement or current of the water. Those all change the amount of, or the rate of corrosion, I should say. So the impressed current system is something that can adjust, all right, and allow us more protection based on its environment. There are 2 types of isolators that you're going to find in use. An older design is the galvanic isolator with what's called a status monitoring system. Now, that was required for older designs to maintain the integrity of the system. And basically, you can see on this right here, there are 2 lights on this one. Green light means the system was working. We had a red light, that means there was an issue with something and it had to be tested. And they also had that remote panel. So again, the boat owner would be alerted possibly with an alarm or a series of lights if the galvanic isolator was not functioning correctly. Newer models are what's called the fail-safe, and the fail-safe system still uses a set of diodes. It's not required to have a status monitoring system because when it fails, it will fail in the closed mode, still allowing any AC fault current to leave the boat through the green grounding wire. So we're all set here with our plug-in, plug-out test. Remember, the reference cell in the water is in the negative, and we have the red going over to the engine negative, or the DC ground bus, whichever is closest or whatever we can get easiest to. And what we want to do is, with the reference cell in the water, we want to get a measurement. And right now, this plug-in, plug-out test, we've got the shore power cord disconnected. So the reference cell's in the water, we're hooked up to the DC negative, but the shore power cord is not plugged into the dock wiring. And what you're seeing is our measurement of about negative 0.742. So that's our reading, and now what we need to do is go and take that shore power cord and plug it in. And what we're looking to see is that reading change very little. You know, ideally we want to see no change, very little change. If there's a substantial amount of change, that may be a sign of an ineffective galvanic isolator, a galvanic isolator that's just not working, and in some cases it just might mean that your boat has a isolation transformer on it. So that's the boat plug-in, plug-out test. Okay, so we've plugged into the dock now, and we see that our numbers are pretty close, which is indication that everything is okay on board in terms of galvanic isolation. So that's where we want to be. And again, if those numbers appreciably change, it may be a sign of that galvanic isolator having an issue, and that is something else you'll have to test.